you need to find a circuit that visits every vertex in the graph and also has the least cost. Okay, and again, to make it a decision problem, we'll say, does there exist a circuit that visits every vertex, right, exactly once, and has an edge cost less than or equal to some quantity. Okay, so this is how we make traveling salesman into a decision problem. Hamiltonian cycle is simpler than, it's essentially the same, but it is at least intuitively somewhat simpler because we are not asking, there is no cost criterion, right? It just says, does there exist a circuit that visits every vertex exactly once? Okay. Yeah, there is this concept of Rudrata cycle, which comes from chessboards and knights. So you probably have heard of this problem of making knight's tour problem, right? So the idea is that, is there a way to take a knight on a chessboard and make it visit every square on the chessboard, right? So you can think of it as a graph problem, right? So you have so if you so a knight here can visit these squares, right? And if you make a graph where each square corresponds to a vertex in the graph, then this vertex will have 8 neighbors, right? So that's how you convert a knight's tour problem into a graph problem, right? And if you do that, then the question you're asking, whether the question of visiting every square in a chessboard is equivalent to finding a Hamiltonian path, right? Hamiltonian path through that graph. Okay. So, and of course, it doesn't have to be limited to an 8x8 chessboard. You can ask, is there a tour on this 16x16 chessboard or arbitrary sized chessboard? Does anybody know how hard that problem is? Knight's tour. Has anybody tried to program a knight's tour in there when they started learning programming? No? Interesting. But see, when I started programming, that was my, that was the second, interesting program that I wrote. The first one was to do queens, which is, compared to the knight's tour, finding a way to put 8 queens on an 8x8 chessboard is a lot easier, right? It's just almost trivial, right? Okay, so none of you have ever tried this problem of finding a tour for the. Yes, you can use backtracking, but if you have a backtracking solution, you'll find that no matter how small the chessboard is, your program doesn't terminate, right? So, but it turns out that there is a very simple heuristic that actually makes your program work very fast. Well, in fact, it finds the solution in the first attempt. Okay, and in fact, it looks like a heuristic, but people who have more CPU cycles and more math abilities have actually proved that this heuristic is going to solve the problem quickly. The heuristic is very simple, right? Suppose you're here, okay, and you need to figure out which of these 8 squares to visit, right? And the objective function that you use to make this decision is to say, okay, let me find how many of these, for each of these squares, let me find out how many of its neighbors are visited. Okay? So I'll ask, okay, how many of this square's neighbors are visited? Maybe this is 3. Maybe for this I have 5 squares from which I can get to this, because 5 of these squares, its neighbors are unvisited, right? And for this one, maybe there is only 1. Okay? And so what's the heuristic? Use the minimum, right? The minimum, because you know that if it has fewer neighbors, then the chances of getting back to that particular square is it's going to be hard, right? So you want to pick the one that has the minimum number of neighbors that haven't been visited, right? And you do that and you get an efficient solution. So although we talk about Ritaka cycle, unless you think about the cycle in the context of a general graph, okay, the Knight's-Tour problem itself is polynomial time, solvable polynomial time. So yeah, longest path is another version of the same problem, because what is the longest path in this graph? Well, the longest path will be a Hamiltonian cycle, right? A Hamiltonian path, which will be something that just doesn't complete the last line, right? It has to visit every vertex in the graph, but doesn't go from the first to the last or the last to the first, right? Balanced cuts. So we looked at this global min cut problem, right? And we had this discussion that it can produce sort of degenerate cuts, where all you cut off was this one vertex, right? So the global min cut might just tell you, okay, you cut off these 2 edges, this one vertex will be disconnected from the rest of the graph, okay? But suppose, and we know that we had an efficient algorithm, clearly a polynomial time algorithm to solve the problem. But suppose somebody tells you, I don't want those degenerate solutions. I want something that kind of cuts the graph in the middle. Okay? So we need to say what middle is. Well, basically, what we are saying here is, if I cut it into 2 parts, neither of the parts should be less than a third. Okay? Because I can't say less than a half, because that means exactly one solution, right? If I said it has to cut it into equal halves, well, that's asking for exactly one cut, right? So what I want is sort of more of what is called a balanced cut, where there is the 2 parts of the graph, they have roughly the comparable size. So this is a hard problem. Integer linear programming, where it's basically exactly like linear programming, except that you put the additional constraint that all solutions have to be integers. Okay, so that's the problem you have, and for many problems, once you insist that the solution is an integer, it becomes hard. Okay, so what are some examples? Well, we have seen knapsack, right? Fractional knapsack was easy to solve, polynomial time. Integer knapsack is not solvable polynomial time. Okay, or take these types of equation x to the power n plus y to the power n equal to z power n. Well, it's trivial to solve these in the real field. But once you say x, y, and z have to be integers, it's very hard. 0, 1 equations is a further, you constrain the integer linear programming further to say that the solution should be either a 0 or 1, not any arbitrary integer, but just 0 or 1, right? And you might think, well, this simplification might make the problem easy, but as it turns out, that even the 0, 1 equation is also very hard. Right? 3D matching. We have talked about bipartite matching and perfect matching, where the idea was that you want to, and again the example we used is often a pairing of men and women, right? And here in 3D matching, we can look at pairing of a man, woman, and a pet. Okay, and then there is compatibility notion. So, for instance, what this triple tells you is that Chet and Beatrice are compatible, and both of them are compatible with the canary. Okay, canary being a bird, right? So that these three can be together, right? And you can see that Chet can either go with Beatrice or Carol, and that Chet can go with either a canary or a bobcat. Okay, so now you need to find, in 3D matching, you need to find perfect three-way matches. Okay, so each person can be paired with multiple, each man can be paired with multiple women and multiple pets, and the same way with each woman. And the question is, can you find a way of finding a suitable match for everyone so that everybody is matched, right? The notion of perfect match still remains the same. Everybody is matched, okay? And everybody is matched with exactly one partner, right? And this is also, again, bipartite matching is solvable in polynomial time using max flow algorithm, whereas here the 3D matching problem is actually NP complete. Okay? Independent set is another hard problem. What's an independent set? Does this graph contain a set of at least k vertices with no edges in between them? Okay, so the notion of independence is no edge in between them. So can I find a sufficient number of vertices that are not connected to each other? Okay, and again, this is a hard problem. Vertex cover. Well, again, if you look at this example, right? So a vertex cover asks, does this graph contain a set of k vertices that cover all edges? Okay, so obviously, if I set k to be, n, well, obviously the answer is yes, right? Only when I make k small, the problem becomes hard, right? So, so in this case, you can think about what is the smallest size vertex cover for this. So again, all the edges need to be covered, right? So it's not the entire set. It's definitely not the entire set. Okay? But anyway, you can think about it. I don't remember the solution, and it's when you don't remember, it takes more than a couple of seconds to figure out the answer. So a clique, okay? Clique means, does this graph contain at least k vertices that are fully connected among themselves? Okay? So there's a subgraph that's fully connected. Okay? So again, if k is very small, like 2 or 3, well, you can enumerate all possible combinations in polynomial time and check it, right? But if k is large enough, then finding whether there is a clique of size k is a hard problem. So again, there is a table, and the reason why I put this table up here is because there might be problems which seem somewhat similar, but one of them is hard and the other is easy. So 3SAT. So 3SAT is a specialization of the SAT problem where each clause has only 3. Okay, so this is actually an example of 3SAT. Okay, so 3SAT is hard problem. Okay, but if you say 2SAT, where each clause has only 2, well, that actually is quite easy to solve. Okay. Again, traveling salesman, that problem is very hard. Okay. Minimal spanning tree is in some ways related, and in fact we'll see how approximate solutions to TSP can be found using a minimal spanning tree, and minimal spanning tree can be constructed very efficiently. Again, longest path is NP complete. It's an example of Hamiltonian path, and shortest path we have seen fast algorithms for that, right? 3D matching and bipartite matching, we already talked about that. Independent sets in graphs is a hard problem, but if you try to find independent sets on trees, that's actually solvable in polynomial time. And again, integer linear programming is hard, but linear programming is not. Right? Linear programming where variables take real values, that's easy. Hamiltonian cycle is hard, but Euler path is easy. Right? So Euler path means you take every edge once, right? And there's a homework problem where I asked you to deal with finding Euler path, right? And there's a simple criteria for determining whether there is an Euler path, and if it does, you know how to find it. And again, Knight store, as I said, is a very similar problem, but somehow it has a very efficient solution. But Hamiltonian cycle in general doesn't have a good solution. And balanced cut and min cut, some of the problem, right? So if you wanted a global min cut, well, that's easy to solve. But if you want the cut to be balanced, that is actually hard. Okay. So now, how are we doing these? Showing that some of these problems are very hard. We are using this polynomial time reduction that we talked about. Here is just the same concept is illustrated with the picture. So you are given a problem instance I, and so what you're doing is you're trying to show that if there exists an efficient algorithm for B, then you can use it to solve problem A, right? So the way you do that is that you take an instance of problem A, and then you say, okay, this is how I convert this instance of problem A into an instance for problem B. Okay? This conversion is being referred to as a function f. Okay? So once you convert that, and then you can feed it in, and the solution comes out. Once the solution comes out, well, you also need to tell how, from the solution to the problem B, you can reconstruct the solution to problem A. Right? If you couldn't do this, well, then you haven't done the reduction, right? Because yes, B could be solved, but if that doesn't lead you to a solution for A, then you haven't proved anything, right? So you really need to do this sort of an inversion function that tells you, okay, how to obtain from the solution to the problem B, how do you get back a solution to problem A. And once you do that, then you have a full reduction, and you are able to show that B, if B can be solved in polynomial time, you can solve A in polynomial time. Once again, never forget, we are proving that B is NP complete by taking a known NP complete problem A and reducing it to B. Okay, so the first NP complete problem showing that it's NP complete, somebody has already done the hard work for you, so you will never have to do that. You always are going to take a known NP complete problem and reduce that to the problem that you want to show to be NP complete. Right? So the problem you want to show to be NP complete is the problem B, and the known NP complete problem is A. So this is some of the reductions that we will try to discuss to some extent. So all of NP, we already discussed how to convert that into SAT. SAT to 3-SAT and a few other reductions will show. Okay, so the arrow here shows the direction of reduction, right? So all of NP, how to reduce it to SAT, I gave you some intuition, right? And we'll not get into this in any more detail at this point. Okay, so 3-SAT from SAT. Okay, suppose you're given a general instance of a SAT problem where there is no limit on the number of variables in each clause, right? So this could be 1, 2, 3, 4, 500, doesn't matter. And that you convert into this form. Well, it's actually quite easy to do this because, you see, if someone gives you a clause with, say, 4 literals, you can convert it into just into two clauses that each have 3 literals. Okay? So look at this formula, right? So you have y1 here and y1 bar here, right? So if you want to make each of them true, you are not going to be able to do that by setting y1 to true or y1 to false. Because if you set y1 to true, then this will be true and this will be false. Therefore, either L3 or L4 would have to be true. Right? So on the other hand, if you set y1 to be false, then this whole thing will be true. But in order for this to be true, either L1 or L2 have to be true because y1 is false. Right? So essentially what this formula has allowed you to do is to say, to express the notion that one of L1, L2, L3, L4 has to be true. Right? Only then this conjunction will be true, and that's exactly the meaning of this class that has 4 literals. Right? So this way we can take any class that has any number of literals and break them up into clauses that have 3 literals each by simply introducing these intermediate, connecting variables like y1 and y2 and so on. Right? So then we'll be able to break up any class with any number of entries into those that have only 3, and then you can always another thing that matters, of course, you shouldn't increase the problem by more than a polynomial size, right? So obviously all we did here is you can see that from a class I will produce, if the class has k literals, well, I'm going to produce k clauses, right? So it's polynomial, right? In terms of the input size, I have an increased exponential, right? So I have a simple construction of a simple way to take any problem, right? Again, keep in mind, we want to show that 3SAT is NP-complete. So we need to take a known NP-complete problem, which is SAT, and we want to show that this known NP-complete problem, SAT, can be converted into an instance of 3SAT. And that's exactly what we did here. Reducing 3SAT to independent SAT. This is a little bit harder because independent SAT is a graph problem, right? SAT to 3SAT is easy because both were satisfiability problem, and all we needed was some, simple variable twiddling here, and we got the answer. But if you want to show that independent SAT is NP-complete, well, we have to start with only, because so far we've only shown SAT to be NP-complete, right? SAT and 3SAT. So we are going to take 3SAT. And once again, you might ask, if I know, why did I bother to prove that a special case of SAT is actually NP-complete, right? I already know general case of SAT is NP-complete. Why did I even bother to do what we did in the previous slide? Simply because proofs are sometimes easier when you constrain the problem in some way, and so that's the only reason. So we can take, what that allows us to do is to take an independent SAT problem and convert it into an instance of 3SAT, which allows us to construct the graph in some simple way, right? So the way we are going to do is, we are going to convert, again, what we are given is, right, we want to show that independent SAT is NP-complete, which means that we have to take 3SAT and reduce it to independent SAT. Okay? So we take 3SAT, so again, it's easiest to understand this construction using an example. Let's say that is the formula, 3SAT formula, and you can convert it into an independent SAT problem in this way, where you construct a triangle, right? So you have x bar, y, and z bar, right? X bar, y, and z bar. Well, you're going to make vertices called x bar, y, and z bar. Put them, arrange them in a triangle. Okay. So now, what is the reason why you are arranging them in a triangle? Because if you pick one of those vertices, right, then that is going to prevent you from picking the other two, right? Again, what is an independent set? An independent set consists of vertices that are not connected to each other, right? So if this vertex is going to be part of an independent set, then these two will not be included. Okay, so that's how. So again, in 3SAT, what are you going to do? You're trying to pick in each clause, which one are you going to set to true, right? So that's exactly what you're trying to do. Find one variable that I can set to true. So if the independent set picks this vertex, okay, that means then you can say that's the same thing as setting y to true. Okay. Now the catch, of course, is that in the SAT problem we have this notion that if x is true, x bar is false. Right? Here in the graph, you notice that there are, x bar is here, x is here, and then x occurs again, x bar occurs once more. So the number of nodes corresponding to each variable, there could be many nodes in the graph. So you need to make sure that the assignments are picked consistently. So for instance, if you pick x to be true here, well, then you should set x bar to be false. Again, that is ensured by connecting x and x bar with an edge. Once again, what that means is that if the independent set chooses x, because x bar nodes are connected to x nodes, so the independent set cannot include the x bar. Right? So this is how we are in this construction able to impose the constraint that x and x bar cannot be true at the same time. Okay? So once we do this, well, then we have we can show that in fact if there exists an efficient algorithm, or if there is whatever solution is there for this to pick an independent set here, that independent set will also end up being a solution, will end up being a satisfiable assignment for the 3-SAT problem. Okay, and that's how we get to show that independent set is NP complete. Okay, now going back. So we have done all of NP to SAT, SAT to 3-SAT, and we have done independent set. We'll very quickly cover vertex cover and clique because they are actually trivially reducible. Okay. Now independent set to vertex cover. Well, it's very simple because if a set of vertices are if S is an independent set, then V minus S is a vertex cover. Because, so notice that if S is an independent set, that means there are no edges between them, right? Which means that every edge in the graph, okay, is connected to some vertex outside of this independent set, right? Because no two vertices in the independent set are connected together, which means that every edge in the graph goes from one of the vertices in the independent set to one of the vertices that's outside the independent set. Which means that if you just pick all the vertices that are outside of this independent set, that will be a vertex cover. So this is how, once you have a solution for independent set, you can have a solution for vertex cover. Now, clique has a similar simple interpretation, right? If S is an independent set, then it is also a clique in the complement of the graph. Okay, because what if we say, what's the complement of a graph? The complement of a graph is obtained by taking, you take two vertices u and v. If there is an edge in the original graph, then there is no edge between those vertices in the complement graph. If there is no edge, then the complement has the edge. So you just you flip the edges, right? Wherever there's an edge, you remove it. Wherever there's no edge, you put a new edge. Okay? So in the case of independent set, what you're saying is that in the original graph, there are no edges between any two vertices, which means that in the complement, every vertex in the independent set should be connected to every other vertex in the independent set, right? So that's why, once again, there's a very simple, very trivial reduction. Okay. So we're not going to go through and show, how to cover the right-hand side. Well, the proofs are a little bit more involved, and we don't have the time to go through them, so we won't bother to go through them. Okay, so let's just finish up by talking about classes that are even beyond NP. Okay, so there is a class of problems called P-space. Okay, P-space means the set of problems that can be solved using polynomial amount of space. Okay, the amount of time is not considered. Okay, you can take as long as you want. Okay, but as it turns out, you cannot take really more than exponential amount of time, because to somehow not go into a loop, you need to somehow remember what you have done so far, and then you need to remember what you have done so far. You need at least logarithmic amount of storage, which means that you can't spend more than exponential amount of time while you're using polynomial amount of space. Okay, so one of the things about space is that it is reusable. So, for instance, we talked about the for all problems, right? For all problems could be solved in polynomial space, although they probably take exponential time, right? Because you're going to, let's say we have this thing and we are asking, is this false for every truth assignment? Well, you can enumerate each of them, and it only takes polynomial amount of space, right? You just need to say, okay, I'm going to try all of them to be 0, and then I'm going to change one of them to be 1, and then the next one to be 1. So it's like counting. It's a binary counter, and it does not going to take you more space than the number of variables, right? So it's going to be only polynomial amount of space. So, of course, you'll find that all NP problems are in p-space because you can verify them in polynomial time. Well, of course, you can do only polynomial space to even search through them. So, again, we can define p-space hard the way we define NP hard. Okay, p-space hard means any problem in p-space can be solved efficiently if a p-space hard problem can be solved efficiently. Okay. Same way we can define p-space complete. Essentially, the hardest p-space problems are p-space complete problems. Okay. We think NP is a subset of p-space, but unfortunately, we are not able to prove. Okay. Then we can talk about exponential time. Okay. After p-space is the next class is exponential time. Okay. So the problems that can be solved in order of 2 to the power n to the power k. Okay, that's how exponential time is defined. Okay. We can show that p-space is a subset of exponential time because, once again, if you have only polynomial amount of memory, you cannot, go through exponential amount of time without revisiting the same state again. And if you revisit the same state, then you are in infinite loop, right? So we don't have a terminating algorithm. So the moment you have a terminating algorithm that takes exponential amount of time, you need at least p-space storage. So, we use the same notion of hard reductions. And once again, we take p-space is a strict subset of exponential, but the only thing we are able to prove is that p-space is a strict subset of exponential, right? So in general, we have this hierarchy of P, a subset of NP, a subset of p-space, subset of exponential, subset of non-deterministic exponential, subset of exponential space, subset of doubly exponential time, subset of non-deterministic doubly exponential time. So obviously you can just keep building this. And what we are able to show is, we are not able to show that P not equal to NP, we are not able to show P not equal to p-space, but we are able to show that P not equal to exponential time. So things that are 3 positions apart, we are able to actually prove that they are not equal. Right? For the rest, we just believe that they are not equal, but we are not able to prove. Okay? So, that wraps up the discussion of NP completeness topic.